अच्छा, ये स्क्रीन नजर आ रही है आप लोगों को? हेलो।
जी सर।
अच्छा, दूसरा, ये अनाउंसमेंट आप लोगों ने पढ़ ली है जो एक दो दिन पहले हुई है अगले वीक से? क्या अनाउंसमेंट हुई है बताएं मुझे। कि अभी जो कैंपस में क्लासेस होंगी वो मैंडेटरी है, which means के it is not necessary that I will provide the video, ठीक है ना? ये सारी लेक्चर्स इसके बाद क्लासरूम में होंगे, बोर्ड वाइट बोर्ड पे होंगे। वाइट बोर्ड पे जब होंगे तो जब क्लास में नहीं होगा उसको सीरियस किस्म का डिसएडवांटेज होगा, ठीक है? तो from the next week things will change. So let's continue. ये मैं यहाँ से एक काम करता हूँ कि जो लास्ट आपको याद होगा, जो लास्ट एग्जाम्पल था वो बुक में, चूंकि वो लेप्लास ट्रांसफॉर्म यूज कर रहा है तो उसमें बहुत आसान हो जाता है उसको डिराइव करना फाइनल इक्वेशन को। लेकिन मैंने बताया था कि नहीं, हम इसको डिफरेंट तरीके से करेंगे। सो जो मैंने ट्राई किया वो ये है कि आई स्टार्ट विद दीज टू इक्वेशंस, आई जस्ट ऐड द टू। तो और व्हेन यू ऐड द टू देन यू सॉल्व फॉर वाई। सो वाई के लिए एक्सप्रेशन आ गया, and then you just substitute that expression in the second equation, ठीक है? And when you simplify this you get the final. So it means that to get the final differential equation you don't need to uh, use Laplace transform, ठीक? ये एक चीज जो है ना, टेक होम इससे ये है, it's not necessary to use Laplace transform. Another thing which you need to notice, and this may help you in uh, solving the end semester problem, yeah, which Maria just uploaded. So let's say you want to solve this by that method, and there are two methods: the energy method, Hamiltonian, and the other is Lagrangian. Okay, you know all the details, and both of them start with the kinetic energy and the potential energy. Okay, so what is the kinetic energy in this problem? There is only one mass here. Okay, so it will be half m x dot squared. There is no rotation, so that's the only energy. The potential energy is the two springs, okay? So half k1 y squared plus half k2 x squared. अब मुझे बताएं ये जो c है इसकी एनर्जी कहाँ आएगी? काइनेटिक एनर्जी में आएगी या पोटेंशियल एनर्जी में आएगी? बताएं। इसकी जो एनर्जी होगी वो कहाँ पे आएगी आपके ख्याल में?
पोटेंशियल एनर्जी सर।
तो जो डैम्पिंग है वो पोटेंशियल एनर्जी आपके ख्याल में होगी, ठीक है? और इसका सोर्स क्या था बताएं? इसका सोर्स क्या था? विस्कोसिटी, फ्लूइड फ्रिक्शन। तो फ्रिक्शन की अभी तक आपने सुना है कि फ्रिक्शन की एनर्जी स्टोर्ड होती है? चलो मैं आसान बना देता हूँ ना। आप सर्किट में आपके पास ये डिफरेंट कंपोनेंट्स होते हैं ना, आर होता है, एल होता है, सी होता है। आपने एनर्जी स्टोर्ड इन कैपेसिटर सुना होगा, ठीक है? हाफ सी वी स्क्वायर्ड। इंडक्टर क्या है? हाफ एल। आपने कहीं सुना है कि रेजिस्टर में कितनी एनर्जी स्टोर्ड होती है?
नहीं सर।
क्यों नहीं सुना? वजह क्या है उसकी?
सर क्योंकि रजिस्टर एनर्जी स्टोर नहीं करता,
वो डिसिपेट करता है, ठीक है?
यस सर।
तो रेजिस्टर के लिए आप सिर्फ पावर की बात कर सकते हैं क्योंकि पावर डिसिपेट होता है। तो एग्जैक्टली मामला सी का है। सी के लिए कोई एनर्जी स्टोर्ड नहीं है, ठीक है? समझ आ गई बात? अब क्वेश्चन ये है कि फिर हम इसको इंडिकेट कहाँ पे करेंगे, ठीक है। अगर यहाँ पे नहीं है, ना V में आ रहा है ना K में आ रहा है, तो वो C की रिप्रेजेंटेशन कहाँ पे होगी, ठीक है। तो उसके लिए क्या है कि लेट्स से आई वांट टू गो फॉर हैमिल्टोनियन, ठीक है, क्योंकि वो आसान होता है, ऑल्दो यू कैन डील विद लैग्रेंजियंस एज वेल। सो हैमिल्टोनियन में हमारे पास दो तरीके हैं। एक तो ये है कि डेल्टा H इक्वल्स टू द वर्क डन बाय नॉन कंजर्वेटिव फोर्सेस, एक ये तरीका है। The other alternative is to go for H dot, yeah, H dot, which will be K dot plus V dot, and this should equal to the work done by the power. W dot is the power. The power associated with non-conservative forces or moments or whatever you call. अब non-conservative इसमें कौन सा फोर्स है इस सिस्टम में, बताएं। ये आपके पास फ्री बॉडी डायग्राम है, ठीक है। एक ये फ्री बॉडी डायग्राम है, एक ये है। इनमें नॉन कंजर्वेटिव फोर्स कौन सा है? नॉन कंजर्वेटिव का मतलब ये है the force whose work done cannot be recovered, okay, it gets lost, तो फिर वो ये फोर्स हो गया, ठीक है, ये वाला। ये भी है, लेकिन ये जो यहाँ पे मास नहीं है, तो this cannot, when there is no mass, this cannot perform any work here, but this one can। तो यहाँ पे क्या हो जाएगा कि आपके पास basically the power is the force, non-conservative force, and the dot product with velocity। और velocity यहाँ पे क्या है उससे related? Relative velocity, क्योंकि इससे associated जो velocity है वो relative है। So and you know if nc is equal to this term, so now this is how the power associated with the damping element enters the equation। it is relevant only in H dot because H dot will require a power, ठीक है। तो इसको डिफरेंशिएट करें और यहाँ पे आप प्लग करें। ये इसको मैं सॉल्व नहीं करने वाला, लेकिन दिस इज हाउ यू विल बी सॉल्विंग दैट इक्वेशन। सो लेट्स गेट टू दी टुडेज लेक्चर, क्योंकि ये पिछला था। And this is a little bit more complicated. Example 4.4.6, so you have two masses, two springs, two dampers, okay, and because there are two masses, so you need two displacements, and by making assumption about which one of them is larger, so let's say if you assume that x2 is larger than x1, that would mean that you are trying to stretch spring K2 downward and damper C2 downward. So in reaction to that, they both will offer these forces. They are reactive forces, okay. One is a restoring force, one is a resisting force. Remember, reacting force can either be a restoring force from a spring, from a damping we call it a resisting force, okay. In both cases you can call them a reactive force. And the so in that respect, the force from M1 from these springs and these dampers on M2 is this, and because the other end of these components, the elastic component and the damping element, are attached to M1, there you will have the opposite direction, because the spring, you know, the two ends of the spring will have that action reaction pair, okay. So if this force is upward, the restoring force, this restoring force will be downward, you can see it there. This will always be the case, okay. स्प्रिंग और टेम्पर में जब आप एक एंड का फोर्स डिटरमिन कर लेंगे, उसका डायरेक्शन, दूसरा आपको दोबारा सोचने की जरूरत ही नहीं है, ठीक। एंड ऑफ कोर्स in the case of M1, if you assume x1 to be positive, because this time you are comparing with this, वो reference है, उसकी velocity 0 है, so you are comparing with 0 only, so you are stretching the spring downward and the damper downward, so उनका भी reacting force जो है ना opposite होगा। And with this you can now start writing the equations of motion. So first write it for M1 and then write it for M2. For M1, I'll start with M1 x1 double dot, and for M2 it will be M2 x2 double dot. So that's a good starting point. For M1, these are the forces which are in the same direction as x1, so they will be positive. So let's write them as positive. K2 x2 minus x1 plus C2 x2 dot minus x1 dot. And these two forces have the opposite direction to x1, so they will be negative. So K1 x1 with a minus sign, C1 x1 dot with a minus sign. Same goes for M2. For M2, F is in the same direction as x1, so positive, and the other two will be negative. K2 x2 minus 1 minus x1 minus C2 x2 dot minus x1 dot, and you can leave it that. These are the equations of motion. And because there are two independent variables, you don't need to simplify it to a single equation. Okay, now we solved a related problem, and this is problem 4.5.2. So the input force is F, which is applied to M2, and it's in the same direction as x1, x2, so you can see that. And the outputs are x1 and x2, the two displacements. X1, x2 are the outputs, okay? Which means that your equation should be in terms of x1 and x2. It doesn't need to be mentioned. When you say these are the outputs, the equations must be in those variables. Now the equilibrium position when f is equal to 0 correspond to x2, x1 equal to 0. इसका मतलब है कि जो x1, x2 है, they are both measured from equilibrium. So that simplifies things for us. Neglect any friction between the masses and the surface. तो यहाँ पे जो friction है उसको हम ignore कर लेते हैं, ठीक है? Derive the equations of motion. अब यहाँ पे क्या है? We can apply an approach similar to this problem. So let's say I start with M1. So M1, and here I will have M2. So if I assume x1 to be less than x2, and that assumption is based on the fact, although it's not necessary, that f is applied to the right. This is just to make myself convinced. Otherwise, I don't need that. X1 can be assumed to be greater than x2 as well. So if x2 is greater than x1, the damping element and the spring element will be, that end will be pushed towards the right. Okay. So on M2, the forces will be opposite, reacting forces. But the same forces on M1 will be in this direction. So make sure that these two are, and these two are opposite, okay? Maybe for your convenience, just to make sure that you are following the discussion, we can draw these diagrams in this way. Let me draw M2 here and M1 here. And I'm not showing these springs in the damper. So when x1 is less than x2, these two elements are being, from this end, stretched towards the right. So the forces will be in this direction, and the corresponding forces on M1, because they are on the other side, will be on this direction. And I can write single terms now. It will be C2 x2 dot minus x1 dot, because that's the assumption. And I also assume that x dot, x2 dot is greater than x1 dot. And the other force will be K2 x2 minus x1. Okay. And this is F. And here, if I assume x1 to be positive, these two elements are pushed towards the right. So the reactive forces will be towards the left. So that is C1 x1 dot and K1 x1. And now I can write down the equation for M1 and for M2. So for M1 it will be easy. M1 x1 double dot, and for M2 x2 double dot. और आपको पता है कि कौन से पॉजिटिव हैं. These will be negative, these will be positive in this equation. In the second equation, F will be positive and these two will be negative. Okay, so this is very similar to this problem. और यहाँ पे आपने नोट किया होगा कि although it's vertical M1 M2 के weights भी होंगे M1G M2G, लेकिन हमने वो इसलिए नहीं किया कि हमें पता है कि हम इंक्लूड कर भी लेंगे तो वो जो है ना वो जो static deflection ultimately we have seen it in many examples that those effects are cancelled out. So the final equation will not have those terms anyway, so why should we bother about that? शुरू में हमने इसलिए किया था कि हमें जरा realization हो जाए. So let's move on to the next problem. It is pretty similar. The only difference here is that you don't see an explicit force like this. यहाँ पे force explicit था, force was the input. Here force was the input. Now in this problem, it can be seen that this end, this is massless, okay? This body is massless. And this rigid body, which is massless, was only used to provide a displacement input. So you can use a displacement as an input. We have seen that in some examples. And remember, this assumes that some mechanism like the cam drive mechanism is responsible for that. अब ये displacement कैसे generate हो रही है, उसके लिए क्या mechanism है, वो हमारे problem का हिस्सा नहीं है. That is the external world. ठीक है ना? So we take that as the input, and then we can now the output is x, so we need to write down the equation in terms of x. Y is the input. The equilibrium position corresponds to x1, x equal y equals 0. So when the input is 0, the output is also 0. That makes sense. Neglect any friction, derive the equation of motion. So because this is the only non-zero mass, so we will start with that, and we can see that because it will, if I assume x to be positive, this spring will be stretched towards right, so the reacting force will be towards left, K2x2, not K2x, sorry, K2x. Now this, if I assume y to be greater than x, yeah, so that means that, or maybe I can, for simplicity, I can assume x to be greater than y. So that means that I am trying to relative to that, and I am trying to push this end towards the right, and the force will be in the opposite direction. Yeah. Or if I make the opposite assumption, if I assume x to be less than y, then this end is going to be stretched towards the right. So the spring will have a force opposite to y. The damper will have a force opposite to y. This is for the rigid body, which is massless. And you know, because this mass is on the other end, so the corresponding force on this side will be opposite. And now we can ignore this because we know that is massless. Okay. So when y is greater than x, then this is the force. So that is k1 y minus x and c times y dot minus x dot. And now we can write down the equation of motion for m. So mx double dot will equal, these two are positive because they are in the direction, k1 times y minus x plus c times y dot minus x dot, and this will be negative, minus k2x, and that is your equation. Very easy. In this problem, you have a crankshaft and a Howdaly damper, maybe this is a type of damper, which is a device attached to an engine crankshaft to reduce vibrations. You know why dampers are used to reduce vibration. The damper has an inertia ID. The damper का अपना inertia है. Remember, it is very similar to those real springs. ठीक है? Real spring का आपको पता है कि उसका inertia भी होता था. यहाँ पे इस damper का भी inertia है, because it's a real damper. that is free to rotate within the enclosure filled with viscous fluid. The inertia IP is the inertia of the fan belt pulley. So डैम्पर के अलावा जो रिजिड बॉडी है उसका जो inertia है वो IP है, ठीक है. Model the crankshaft as a rotational spring. So you model the crankshaft as a rotational spring, this one, KT. And because it has inertia, so we must not forget that inertia. That inertia has been shown separately, okay? And we have shown inertia IP separately. वो जो बाकी rigid body है, ये damper के अलावा, so ये damper, ये other than damper है, other than damper और ये damper है, ठीक है ना? Now ये कहाँ से आया है? अब चूंकि ये डैम्पर है तो डैम्पर का सिर्फ इनर्शिया तो नहीं होगा ना. डैम्पर है तो उसका जाहिर बात है उसके लिए आइडियल डैम्पिंग एलिमेंट भी होगा. तो बेसिकली इसका मकसद तो ये है. सो वी बेसिकली रिप्लेस दिस रियल डैम्पर विद एन आइडियल डैम्पर व्हिच इज CT, and we represent the inertia of that damper separately as a rigid body. So I can say that the real damper has been represented by an ideal damper attached to a rigid body. और उसके लिए let's say derive the equation of motion with the angular displacement theta p for this inertia, theta d for the inertia associated with the damper, and the crankshaft angular displacement phi as an input. This is another example where crankshaft displacement is taken as an input. Crankshaft कहाँ से ये generate करता है वो mechanism हमारा interest नहीं है, ठीक है. So we can now ignore that and we can now deal with this free body diagram or the free body diagram associated with this, ठीक है. So again we have, if we look at this from this side and see all the rotation in a single plane, so we can see that okay, you have one, and let's say we start with IP. So I have this rigid body IP, and I can similarly have a free body diagram for ID. So for IP, I know that this phi is the input, yeah, because if I'm looking from this side, let's say this is my I, so this phi will be clockwise. And if I assume that this phi to be greater than this phi p, so that means that I'm trying to twist the spring clockwise, yeah. So the reaction on IP no, because I want to represent the reaction on IP, so let me assume theta p to be greater than theta phi, okay. So if theta p is greater than phi, I am trying to twist the spring. This body will try to twist the spring clockwise, just like this phi, yeah. And basically I can show theta phi also in that direction. So the reaction to that on IP from KT, that will be opposite. That's इसलिए मैंने ये assume किया ताकि मैं आसानी से लिख सकूं. So that will be KT times difference किसका है, because you assume this, so it will be theta p minus phi, ठीक है ना. And same goes with phi, but here we also assume something. Let's say theta p is greater than theta d. So this means that the action from IP on this damping element is a twist, is a clockwise twist. So the reaction will again be anti-clockwise. which is Ct times theta p dot minus theta d dot. Let me just write it clean. Ct times theta p dot minus theta d dot, and I'm writing this because of this assumption. Okay, that assumption makes everything. That assumption allows you to write this term. That assumption assumes that you are twisting clockwise that damper, and when you are twisting something clockwise, the reaction will on you back on you will be anti-clockwise. अब ये लिखने का फायदा ये हुआ, and similarly we can now क्योंकि हमने CT का लिख दिया है, यहाँ पे clockwise है, तो ID पे उसका रिएक्शन एंटी क्लॉकवाइज होगा, एक्शन रिएक्शन पे. That will be Ct again theta p dot minus theta d dot, और उसका अपना एंगल theta d है. And we can now write down the equation for theta d and for Ip. So for Ip I can write Ip theta p double dot, and for Id I can say Id theta d double dot. Moment equation. Id के लिए तो बहुत आसान है कि there is only one more opposing torque, so that will be minus C1 theta p dot minus theta d dot. और थीटा पी के लिए क्या है, ये पॉजिटिव हो जाएगा, नहीं सॉरी, इस केस में अपोजिट नहीं है, इट्स इन द सेम डायरेक्शन बिकॉज दिस इज क्लॉकवाइज, दिस इज क्लॉकवाइज, तो यहाँ पॉजिटिव हो जाएगा, उधर नेगेटिव हो जाएगा. C1 theta p dot minus theta d dot, and this spring torque is also negative, so Kt theta p minus phi, and phi is positive because phi is in the same direction as theta p. So here we go, we have both the equations. ये scary looks देता है, लेकिन if you have these free body diagrams, you follow some convention, make assumption, that assumption will entail or imply some twist on one end, और ये assumption आप वो करें जो आपके लिए आसान हो. For example, अगर मैं ये less greater than करता हूँ, तो वो assumption मुझे उधर करनी पड़ेगी, maybe that's a bit complicated. So sometimes less than will be easier and sometimes greater than will be easier. आपका जो है ना फ्री बॉडी डायग्राम में कन्वेंशन को फॉलो करना जरूरी है. जस्ट फॉलो द कन्वेंशन व्हिच मेक्स योर जॉब इजियर. नेक्स्ट एग्जांपल. अब इस तरह के एग्जांपल जो है ना, इस यहाँ पे हम दो तरीके यूज करेंगे. एक का मैं सिर्फ स्केच बताऊंगा, और दूसरा कोशिश करेंगे कि वी डू दैट इन अ डिटेल्ड फैशन. सो obtain the equation of motion in terms of theta. हमने थीटा के लिए सब कुछ करना है. Remember, यहाँ पे चूंकि x भी है and we want everything in terms of theta, तो यहाँ पे एक assumption है, अगर ना भी बताया जाए तो assumption हमें चाहिए, वो है no slip assumption. यहाँ पे कोई slipping नहीं हो रही, कि अगर slipping हो गई फिर x और theta independent हो गए, वो हम नहीं कर सकते फिर उसको deal. So that's clear that we are assuming x to be equal to r times theta, and x dot will be equal to r times theta dot. This is the underlying assumption, even if it is not mentioned. So typical ये है, although you don't have slipping, you still will have the tangential force. So let's call that F. और आपको पता है कि if we write down, let's say we write down the force balance for this rigid body. If this is my rigid body M, let's say M, तो पहले मैं इस पे जो है ना forces देख लेता हूँ कि कौन कौन से forces हैं. So if it is moving towards the right, because theta is clockwise, so x will be towards the right. So this will try to push the spring towards the right against that support. The reaction of the spring will be in this direction. So यहाँ पे हो जाएगा k times something. We need to find that something. and it will try to stretch this damping element, and the reaction of that will also be opposite, so that will be C times something. This will be our force, and the other force, of course, is this one, F. Okay. What is this something? We know that this theta is small, so B times theta will give you that tangential velocity. So this will be B times theta, that tangential displacement, sorry. You need that tangential displacement for K. Okay. And for C, you need the tangential velocity. So the same B theta will be B theta dot, because C has to multiply velocity, K has to multiply displacement. Both are linear, tangential. So tangential displacement associated with theta at this point P is B times theta and B times theta dot. Okay, na? Now this will not be enough because we have this unknown force. So we also need a free body diagram for the associated inertia and rotation. तो उसके लिए क्या है कि हमारे पास the now to simplify things, if we take this O to be our origin, and if we want that balance about O, then we have to find the moment of F and to find the moment of these two, and that will complicate things because we have three forces to deal with and three moments. So why not choose P as our pivot? So मैं क्या करूंगा, मैं P को चूज करूंगा और P के अराउंड में जो है ना, I'll go for IP, the inertia, okay, inertia about P. तो उसका फायदा ये हो जाएगा कि I don't have to bother about these two forces, ठीक है ना, because they are crossing P. So I only need to bother about F, और F का force क्या होगा, anti-clockwise. This will be F times अब ये जो distance है, this is tricky because we need from this point, क्योंकि F ने यहाँ apply होना है, तो ये जो vertical distance है यहाँ पे, so यहाँ से यहाँ तक तो R हो जाएगा, ठीक है. So F will multiply R plus B का ये component, ये. So B times, remember this is theta, this angle is theta. So B times cosine of theta. If you look carefully, the component of B which is perpendicular to F is this one, and that is B cosine of theta. So B cosine of theta multiplied by F will give you the only torque, or the torque associated with the spring and this damping element will be zero क्योंकि हमने वहां भी किया हुआ है. अच्छा, मसला ये है कि IP क्या है, IP भी तो करना है ना. IP क्योंकि center of mass उसका O है, so it's much easier for us to know IO from the tables, okay. Plus parallel axis theorem will write M और O और P के दरमियान क्या डिस्टेंस है, B. So MB squared. अब IO क्या है टेबल से, because it is a disk, it is a solid cylinder का हमें पता है कि it's half mr squared. आप इसको चेक कर लें, half mr squared. ये half ना होता अगर ये पार्टिकल होता, क्योंकि पार्टिकल नहीं है, सॉलिड सिलेंडर है. So half mr squared is the inertia about O, but O is not convenient, we go for P. The inertia about P is that inertia plus mb squared, parallel axis theorem. फायदा इसका ये हुआ कि we only need to consider this torque. अब मैं एक इक्वेशन इसके लिए लिखूंगा, force equation, and that is what, m times x double dot equals ये सारे नेगेटिव हैं, तो माइनस एफ माइनस बी सी थीटा डॉट माइनस बी के थीटा। ओके, और यहाँ पे क्या है इसके लिए आई पी, एंड आई नो आई पी ये है, सो आई डोंट नीड टू राइट इट अगेन, आई पी theta double dot, and that equals this force, which is this torque, which is R plus B cosine theta times F times, yeah, so no, times F. अब यहाँ पे सिर्फ एक इशू ये है कि we want everything in terms of theta, so I need to get rid of this x, so यहाँ पे x double dot will be equal to R theta double dot, so now I need to replace this by R theta double dot, and I need to combine these two equations. Why not add it, क्योंकि थीटा डबल डॉट दोनों साइड पे आ रहा है, so it will be आई पी प्लस एम आर इक्वल्स, और ये सारी कहानी यहाँ पे भी लिख दूंगा, ठीक है। बट यू नो दिस इज सो डिफिकल्ट, ऑल्दो हमने कर तो लिया है, लेकिन इट इज वेरी इजी टू मेक मिस्टेक्स इन सच एन अप्रोच। तो इसके लिए हम, आपको याद है कि ऐसे प्रॉब्लम्स के लिए जो ज़्यादा आसान तरीका है वो क्या था, दी एनर्जी मेथड्स। एनर्जी मेथड में आपके पास ऑप्शन है, यू कैन ईदर गो विद हैमिल्टोनियन और विद लैग्रांजियन, वी विल ट्राई हैमिल्टोनियन, सो लेट्स राइट डाउन दी काइनेटिक एनर्जी फर्स्ट। व्हाट इज द काइनेटिक एनर्जी? कोई सजेस्ट कर सकता है काइनेटिक एनर्जी यहाँ पे क्या होगी? ऑफ कोर्स एक m है, तो इसका जो ट्रांसलेशनल पार्ट है that will be half m x dot squared, okay, and that x dot I know is r theta dot, तो मैं भी इधर ही मैं उसको ठीक कर देता हूँ, half m r theta dot squared, ठीक है, that is the translational kinetic energy। rotational क्या हो जाएगी, half I, और अब यहाँ पे मैं आई ओ लिख सकता हूँ, क्योंकि मुझे पता है K और C they will not give me kinetic energy, so I can go back to O, I know, बल्कि यहाँ पे okay, and that will be theta dot squared, and IO I also know is half mr squared, so this is my IO, okay, and I can simplify this, it will be half something theta dot square, you can see that, okay, theta dot square common आ जाएगा और यहाँ पे ये कैलकुलेशन आप कर लेंगे। Similarly, we can now write down the expression for the potential energy, और वो क्या है, I'm just checking if everything is working fine. So potential energy, पहले मुझे बताएं कहाँ से आई ये पोटेंशियल एनर्जी इस प्रॉब्लम में? तो बता सकते हैं पोटेंशियल एनर्जी किस एलिमेंट से आएगी? That will come from K। अब मास के लिए तो हमने दोनों लिख दिया ना, ट्रांसलेशनल भी लिख दिया और रोटेशनल भी लिख दिया। नाउ हाउ डू वी नो कि स्प्रिंग के लिए हमें ट्रांसलेशनल और रोटेशनल लिखना पड़ेगा या नहीं? तो उसका ताल्लुक किस बात से है? इस सिंबल से है। वी नो दिस सिंबल इज ट्रांसलेशनल, सो वी डू नॉट नीड टू कंसीडर टॉर्जनल स्प्रिंग्स, ओके। और ये स्मॉल एंगल ऑसिलेशन का मतलब ये है कि we assume that as far as the spring is concerned, the motion is horizontal क्योंकि angle small है। So we need to write half k, और इसका जो displacement है वो क्या था, हमें पता था, that displacement squared, and that displacement we know was b times theta, okay। So now we have the expression for k, the expression for v, and we should also write the expression for k dot, differentiate this, and the expression for v dot, and we know that h dot will be equal to k dot plus v dot, but this h dot has to equal the power associated with non-conservative elements. Now that will come from C. So वहां पे क्या है, force associated with non-conservative element times the velocity, which is b times theta dot, and that force I know was c times b times theta dot. So ये b times theta dot जो है ना स्क्वायर हो जाएगा, क्योंकि 2 दफा आ रहा है. अब यहाँ पे क्वेश्चन ये है कि why don't we consider this friction, क्योंकि ये भी तो नॉन कंजर्वेटिव है. ये हमने देखा था कि this friction will do, क्योंकि यहाँ पे हमने वर्क पावर देखना है ना, पावर तब होगा नॉन जीरो जब वर्क नॉन जीरो होगा. And this force, this tangential force, the friction force, can perform work only if there is slipping. Slipping चूंकि यहाँ नहीं हो रही है, हमने this assumption का मतलब यह है no slip. No slip का मतलब यह है कि this force cannot do work, and when it cannot do work, we will not have to include it in our equation. तो हमने सिर्फ ये देखना है कि इसका वर्क नॉन जीरो है. ये बात समझ आ गई ये वाली, कि ये फोर्स फ्रिक्शन वाला फोर्स हम तब इंक्लूड करेंगे जब स्किडिंग या स्लिपिंग होगी, और वो इस केस में नहीं है. ठीक है, वो म्यू टाइम्स जो नॉर्मल फोर्स है उससे जब ज्यादा हो जाएगा फिर हम वो टर्म भी इंक्लूड करेंगे. वी आर नॉट इंक्लूडिंग दैट टर्म. अब देखो ना, इसमें when you plug the derivative of k, the derivative of v, and this term, you will directly get your equation. So this is much easier compared to the free body diagram methods. Do you have any question in this? क्योंकि ये अगर आपको समझ आ गई तो आप असाइनमेंट बहुत आराम से कर सकेंगे. ठीक है. Of course, if we had to use the Lagrangian, so Lagrangian will be k minus v, नहीं, yes, k minus v, और हमें पता था कि वो बाद में जो पार्शियल डेरिवेटिव्स आ जाते हैं, और राइट साइड पे आपके पास नॉन कंजर्वेटिव जो है ना वो फोर्सेस आएंगे, नॉन कंजर्वेटिव मोमेंट्स आएंगे. दैट्स यू नो इट ऑलरेडी. Let's move on to the next example, and we have another example of displacement as the input. ठीक है, ये ना भी बताएं तो यहाँ पे पता चल जाता है the input is the displacement y. ठीक है, the output is the displacement x. This is the output. So you need to write your equation in terms of x, and the spring is at its free length when x is equal to y. That simplifies the math. Look at the free body diagram, उसने already दिया हुआ है, और इस एक्सप्रेशन को देख के पता चलता है कि you assume y to be greater than x. When y is greater than x, you are trying to stretch this element to the right. So if this is considered to be a rigid body, a massless rigid body, the spring will apply, मैं इसको यहाँ पे शो कर लेता हूँ, the spring will apply a force towards the left, and because this mass is on the other side of the spring, वो फोर्स टुवर्ड्स द राइट होगा. तो देखो ना, ये मैच कर रहा है उधर टुवर्ड्स द राइट. ठीक है, सो दैट्स व्हाई दिस assumption, या आप लेस देन और ग्रेटर देन तब करें ताकि आप आसानी से ये कर सके. ठीक है, सो नाउ वी कैन से दैट ओके, this is the force from the spring on the mass, and now we make a further assumption. Let's assume x to be positive. So this mass moves towards the right, it tries to stretch that damping element towards the right. The opposing force will be opposite, cx dot. And from here you can write the equation, which is m times x double dot, ky minus x is towards the right, so it is positive because it favors x, and cx dot is negative with a minus sign. I mean, I don't want to say cx dot itself is negative, but it will appear with a minus sign in the equation. The next example is a rotational one. So derive the equation of motion for the system shown. The input is the angular displacement. So there is another example. This phi is the input. It comes from some mechanism which we don't care. And this applies to the shaft, which has this, which is flexible. So uska रोटेशनल टॉर्शनल स्प्रिंग कांस्टेंट KT है, और टॉर्शनल स्प्रिंग लिखा भी है, यू मॉडल दैट रॉड एज ए टॉर्शनल स्प्रिंग, ठीक है। द आउटपुट is the angular displacement theta of the inertia, ये theta of the inertia हो गया। Now the question is whether we need to include the inertia of the rod as well, तो उसके लिए इसने ये लिखा हुआ है कि neglect the inertia of the rod, इसका मतलब ये I इतना बड़ा है compared to the inertia of the rod कि उसको हम ignore कर रहे हैं, ठीक है। And of course there is some damping element associated or between the rigid body and the support CT. So you have a torsional spring, a torsional damping, or I mean, it's not good to call it torsional damping. You call it rotational damping. I have to check whether torsional damping is used frequently. So you have this rigid body I, और यहाँ पे अगर आपको देखना easy नहीं है, so we can say that okay, if I assume if I assume theta, if I assume phi to be greater than theta, which is suggestive of this term, so this means कि यहाँ पे मैं इस साइड पे एक massless जो है ना rigid body assume करूँगा, which is trying to twist this spring clockwise, yeah. So the reaction from the spring will be anti-clockwise, and because the rigid body is on the other end of let's just follow the reasoning. मैं एक hypothetical rigid body assume कर रहा हूँ क्योंकि for me to determine the sign of that torque is easier, okay, and this will be opposite. देखो ना ये arrow और ये arrow, ये अगर anti clockwise है तो ये clockwise है, so this helped me and now I can ignore this, ठीक है। ज्यादा डायरेक्ट ये होता अगर हम ये assume करते, फिर मुझे ये बॉडी assume करने की जरूरत ना होती अगर मैं ये assume करता कि phi is less than theta. When phi is less than theta, then theta is greater, so this rigid body is trying to twist this spring to a clockwise from the right, तो ये फिर जो है ना ये फिर ऐसे होता opposite, and this would have been k times, because this times theta is larger, so it's theta minus phi. देखो ना ये in one go you get that answer, but if you want to go with the book, you assume phi to be greater than theta. For that you need this hypothetical body, and then you get this, okay. It's up to you which one you use. And if because this is zero, the rigid support is at zero rotational velocity, if I assume theta to be positive, this I will try to twist this damping element clockwise, और उसका जो reaction on I, that will be anti-clockwise. देखो ना, clockwise, anti-clockwise. And now everything is ready. Once you get this free body diagram with the correct symbols, with the correct signs, इसके बाद फिर लिखना कोई मसला नहीं है. Moment equation is simply I times the angle associated with the rigid body is theta, so we just write theta double dot, and this torque is in the same sense, so that will come with a positive sign, k times phi minus theta, and this torque is opposite, so this is minus ct theta dot, and that's your equation, okay. And there is no torque in the rod when phi is equal to theta, तो अब ये बेसिकली ये इक्विलिब्रियम है। वैसे इसको आप चेक भी कर सकते हैं, ठीक है ना, इसको आप चेक भी कर सकते हैं। when theta is equal to phi, this term will be zero, okay. So Okay, sorry. What happened? Okay, something pressed by mistake. The next problem. So this is again an example. अब यहाँ पे we have seen something like this before. It's not new. सिर्फ फर्क ये है कि यहाँ पे let me show you that ताकि आप connect कर सके ना. Oh sorry, ये पिछले उसमें था. Let me open that. It was the last example. Okay. Remember, we discussed this scenario where you have a massless rigid body, a point, and you can still have a free body diagram for that. Okay. Yeah. This is the reaction force from the spring. This is the reaction force from the damper. This is the rigid body. और आप उसके लिए जब इक्वेशन लिखेंगे तो इसका मास 0 है तो even if you represent that by with a mass, that mass will be 0. Basically यहाँ पे वो ये करने की कोशिश कर रहा है. I don't think this is a new problem, so we can simply skip that. Okay. देखो ना ये point A के लिए obtain the equation of motion of the point A. अब point A का मतलब ये है कि this is a massless rigid body. तो ये आसानी के लिए आपको समझाने के लिए इसको MA कह देता है, but I don't think you need that. You are used to that. You just consider this as a point with no mass. और चूंकि mass नहीं है तो यहाँ पे basically कोई motion नहीं होगा. So that's 0 times the displacement. और यहाँ पे क्या हो जाएगा? Displacement इसका चूंकि x है, so I'm just writing 0 times x double dot. And that will be this is positive because this is so k times y minus x, and this will be with a negative sign. Okay, and this is your equation. So that's something which you can do easily. Now this is another example where the displacement is applied as an input. Okay, that's clear from the diagram, even if it's not mentioned here, although it's mentioned there. When x1, x2 and y they are all equal, you have okay the springs are at free lengths, derive the equation of motion. So अब यहाँ पे भी आप m1 के लिए फ्री बॉडी डायग्राम ड्रॉ करें, m2 के लिए करें. इस साइड पे रिमेंबर अगर सपोर्ट होता तो फिर इधर भी फोर्स होता. यहाँ पे चूंकि खैर मास के लिए कोई सपोर्ट नहीं चाहिए, सपोर्ट आपको चाहिए स्प्रिंग के लिए. ठीक है, so you don't need a support here क्योंकि सपोर्ट this is a moving mass. Okay, so moving mass के लिए कौन सा सपोर्ट है? So you see the assumption is that if you assume x2 to be greater than x1, so this reaction force is on m1, this reaction force is on m2 with the same magnitude, and if you assume y to be greater than x2, so again you stretch this towards the right. On this hypothetical body it will be towards the left, and on this it will be towards the right. Okay, and then you can write down the equations of motion for m1 first and then for m2. For m1 it will start with something like m1 x1 double dot, and for m2 it is m2 x2 double dot. और आपको पता है यहाँ पे ये पॉजिटिव साइन के साथ इधर आ जाएगा, ये पॉजिटिव साइन के साथ इधर आ जाएगा, और ये नेगेटिव साइन के साथ इधर आ जाएगा. ठीक है. The next example looks scary, but you can simply identify the two rigid bodies. Okay, this first rigid body, the second rigid body. And if you are not comfortable with this diagram, you can draw them. You can look at this in the direction of the axis of rotation, and let's say your eye is here. So then you can draw everything. क्योंकि यहाँ पे कोई translation नहीं है, so you can draw both these bodies in a plane. Okay, in a plane. और यहाँ पे फिर आप ये सारी चीजें शो कर सकते हैं. ठीक है. So consider phi as your input displacement एंड इफ यू assume phi to be greater than theta 1, तो अगेन यहाँ पे वो हाइपोथेटिकल बॉडी होगी, उस पे उसका, क्योंकि यू आर ट्विस्टिंग दिस टॉर्जनल स्प्रिंग क्लॉकवाइज, तो जहां से ट्विस्ट आ रहा है उस पे एंटी क्लॉकवाइज होगा, और I1 चूंकि दूसरे एंड पे है तो उस पे फिर क्लॉकवाइज हो जाएगा, ठीक है, एंड देन यू कैन इग्नोर दिस. सेम गोज फॉर दिस टॉर्जनल डैम्पिंग. तो टॉर्जनल डैम्पिंग में इफ आई assume theta 1 to be greater than theta 2 and theta 1 dot to be greater than theta 2 dot, so I1 will try to twist the damping element clockwise, so the reaction back on I1 will be anti-clockwise, ठीक है, and this means that the expression will be theta 1 dot minus theta 2 dot, whichever is greater, वो positive हो जाएगा. And because I2 appears to be on the other hand side, on the other side of the damper, तो वहां पे ये and clockwise हो जाएगा, ठीक है. The last one, assume theta, क्योंकि सपोर्ट है, सपोर्ट पे जीरो डिस्प्लेसमेंट है, जीरो वेलोसिटी है, so again assume theta 2 dot to be positive. So this rigid body is trying to twist it, the damping element clockwise. The reaction back on I2 will be anti-clockwise with the same expression. और फिर इसके बाद आप क्या करेंगे? You just write down one equation for I1, which is I1 theta 1 double dot and I2 theta 2 double dot. यहाँ पे क्या होगा? क्या क्या पॉजिटिव है? This one is positive because it's in the same direction, in the same sense. And this term will not appear in I2 क्योंकि इस साइड पे रह गया है, ये दोनों साइड पे होगा. So for I1 it will have minus sign क्योंकि it's opposing, and we just copy it with a positive sign क्योंकि हमें पता है कि इधर वो opposite होगा. And that CT1, that CT2 times theta 2 dot is opposing theta 2, so that will come with a minus sign. And here you have both the equations. This is another problem which looks complicated, but again you just need to read the question carefully. So you have a driving disk rotating at a specific speed omega d. ये डिस्क है आपके पास ओमेगा डी. बेसिकली डिस्क ये है, लेकिन जो कि शाफ्ट के साथ है तो ओमेगा डी वहां पे उसने अलग शो किया हुआ है. There is a viscous fluid layer between this disk and the driven disk. इसका मतलब ये है कि एक ये डिस्क है और एक ड्रिवन डिस्क इधर है, ठीक है. ये जो साइड है ये ड्रिवन है और वो ड्राइविंग है, ठीक है. ड्राइविंग साइड और ड्रिवन साइड आपको याद है, जिस तरह हमारे केस में ये तो गियर्स नहीं है, अगर ये गियर्स होते तो वहां पे वो पिनियन और गियर होता, लेकिन यहाँ पे चूंकि गियर्स नहीं है, सो वी जस्ट यूज द ड्राइविंग साइड एंड द ड्रिवन साइड. सो इसीलिए ये WD को उसने उधर ड्राइविंग साइड पे शो किया हुआ, ठीक है. दूसरी साइड पे उसको आप ओमेगा 1 कह दें, ठीक है. Because of the damping element, there will be relative motion between the two, so omega 1 cannot be equal to omega d. Driven disk whose inertia plus that of the shaft is I1. देखो ना, ये important है कि जो I1 आपने लेबल किया हुआ है, this includes the inertia not only of the disk but also of the rod. तो इसलिए rod को आपने massless लेना है क्योंकि इसका inertia यहाँ पे आ गया है, ठीक है. Now through the action of the viscous damping, the rotation of the driving disk causes the driven disk to rotate, and this rotation is opposed by the load torque T1. तो जो रिएक्शन टॉर्क है लोड से, क्योंकि इसने किसी लोड को भी करना है, वो T1 है, ठीक है. ये चेक कर ले कि चूंकि रिएक्शन है तो ये इट गोज अगेंस्ट ओमेगा 1. देखो ना, ओमेगा 1 इज अ कॉन्सिक्वेंस ऑफ ओमेगा डी, एंड दिस ओमेगा 1 is in the same direction, is in the same sense as omega d, क्योंकि उसी को फॉलो कर रहा है, उसी के सेंस को फॉलो कर रहा है, मैग्नीट्यूड जरूरी नहीं कि सेम हो. एंड बिकॉज दिस इज द रिएक्शन टॉर्क, तो ये अपोजिट होगा, ये लोड टॉर्क है. Derive a model for the speed omega 1. अब उसके लिए we have two rigid bodies, I1 and ID. नहीं, I1 you have just one rigid body. उधर तो कोई नहीं है, उधर तो आपके पास सिर्फ ये है ना. This is another example where the input is a velocity. ये जो w omega d है, this is your input, okay? क्योंकि ये स्पेसिफाइड है, ये ओमेगा डी कहाँ से आ रही है वो हम डिटेल में नहीं जा रहे. इसका मतलब कि we are taking this as our input. So motion as an input में कभी आपको जो है ना displacement as an input आएगा, कभी आपको velocity as an input आएगा. यहाँ पे angular velocity as an input है. T1 is not your input. T1 आपका load torque है, disturbing. So if you look at this if this rigid body now, तो of course इसकी अपनी angular velocity है omega 1 और T1 is opposing that. तो ये हमने सिर्फ उसको show किया हुआ है. And because so if I again assume this damping element has been shown separately here as CT, ठीक है ना, and this is a massless body because we don't want to bother there. हमने सिर्फ इस ओमेगा डी को देखना, ठीक है. So if now we need to have some assumption about these two. So if I assume omega d to be greater than omega 1, which is evident from this, or maybe एक और काम कर लेता हूँ मैं. For simplicity, I don't go with that. I just go with my intuition and I say that okay, omega 1 is greater than omega d, ठीक है, क्योंकि मैंने यहाँ पे देखना है कि I1 पे इसका इम्पैक्ट क्या है. So when omega 1 is greater than omega d, this I1 will try to twist the damper clockwise, so the reaction back on I1 will be anti-clockwise. और उसका वो क्या होगा, expression that will be CT times omega 1 minus omega d. अब अगर आप इस डायग्राम में देखें, इस डायग्राम में एक्सप्रेशन इसने उल्टा लिखा है, ओमेगा डी माइनस ओमेगा 1. तो ये चूंकि इससे उल्टा है तो उसका ये एंटी क्लॉकवाइज है एंड दिस इज क्लॉकवाइज, ठीक है ना. सो यू कैन नाउ जस्टिफाई दिस बेस्ड ऑन दैट रीजनिंग एंड नाउ यू कैन रिमूव दैट रीजनिंग, ओके. सो यू कैन ऑलवेज assume a sign which is consistent with your intuition, and later on you can change it if you want. So T1 is again the load torque. This is the reaction torque from the damper. And we can now write the moment equation for I1, which is I1 I1 omega 1 dot, क्योंकि velocity है तो डबल डॉट नहीं लिखूंगा. The reaction torque is CT omega d minus omega 1, and the load torque is with a minus sign, and this is your equation now. And again, if you I'm just telling you that if you don't like these 3D type pictures, you can just look at this from this side and have everything in a single plane, and then you can easily follow all these symbols कि कौन सा plus है कौन सा minus. It's easily identifiable. Okay, this is another example. ये बिल्कुल उसी तरह का है, fluid clutch. It's very similar, ठीक है ना. This time you just have the only difference between these two is that here w omega d was the input, and here you have a driving torque there, Td, that is your input. Okay, so Td is the specified function of time, and T1 is also a specified function of time. This looks like a load torque, and this looks like a applied torque, but both are external torques. Okay, तो आपके लिए दोनों एक्सटर्नल टॉर्क्स हैं एंड द फ्री बॉडी नाउ यू विल हैव और इसमें एक और चीज भी है जो पिछले डायग्राम में नहीं थी कि इसका अपना इनर्शिया है। जो डैम्पर है इस केस में डैम्पर का इनर्शिया कोई नहीं था। द डैम्पर वाज आइडियल डैम्पर massless. In this diagram you have the damper is also has a inertia, तो वो हमने अलग से शो किया हुआ है ID, ठीक है ना। ऑफ कोर्स डैम्पिंग उसकी डैम्पिंग आइडियल डैम्पर तो शो करना पड़ेगा, उसका इनर्शिया भी हमने अलग से शो किया, उधर जो ड्राइविंग टॉर्क है वो भी अलग से शो किया, लोड टॉर्क तो पहले से है। सो यू हैव टू रिजिड बॉडीज, ठीक है, with their associated free body diagrams, ठीक है, and then you can just write down the individual equations. So I don't need to repeat all the reasoning over and over. Let's focus on the problem क्योंकि इसमें थोड़ी सी चीज डिफरेंट आ रही है। ओके अब यहाँ पे यू हैव मास m और ये मास m रॉड का नहीं है, ये कंसंट्रेटेड मास है, ठीक है। इधर इज अटैच्ड टू अ रिजिड रॉड और रिजिड रॉड का इनर्शिया क्या है, वो I है, ठीक है। सो रॉड का इनर्शिया I हो गया, कंसंट्रेटेड मास m हो गया, ये डिस्ट्रीब्यूटेड है, ये कंसंट्रेटेड है। अबाउट द पिवट, दिस इज योर पिवट, ठीक है। नेग्लिजिबल फ्रिक्शन, सो पिवट यहाँ पे कोई पिवट से एसोसिएटेड कोई डैम्पिंग एलिमेंट नहीं है। द इनपुट इज द डिस्प्लेसमेंट c, this displacement is the input. When z theta are 0 the spring is at free length, the standard, assuming theta is small का मतलब यह है कि we are only considering horizontal motion, rotation वाला part हम ignore कर लेते हैं। Derive the equation of motion for theta with z as the input. So theta is our output, z is our input. So how do we go about it? Of course z is the displacement of this end, we need to find the displacement of this end, ठीक है। और पिवट, सॉरी पिवट मैंने यहाँ पे शो किया था, ये पिवट यहाँ नहीं था, सॉरी पिवट यहाँ पे, पिवट ये है, ठीक है, दैट वाज अ मिस्टेक। सो पिवट एसोसिएटेड विद पिवट देयर इज नो डैम्पिंग, डैम्पिंग अलग से यहाँ पे है, वो एट दिस पॉइंट। नाउ वी नीड टू relate the displacement of the spring and of the damping element to theta, और उसके लिए हम वही सिमिलर ट्रायंगल्स वाला लॉजिक यूज करेंगे, सिमिलर ट्रायंगल्स। वो लॉजिक क्या है कि because it's a common angle we can draw this is your pivot and let's say this is the displacement of the spring, ठीक है। जरूरी नहीं कि यहाँ पे हो, इसको कहीं पे भी शो कर सकते हैं। let's say this is this, so we need this first and then we need this as well, और ये तो ऑलरेडी गिवन है। So based on that we can now write down pivot का आप स्टैंडर्ड ले लें। So L1 और लेट्स से इस एंड का जो स्प्रिंग का है ये, इसको आप कह दें, इसको आप y कह दें, let me just see if theta is positive and theta goes in the clockwise direction, m will go like that, so this point will go like that, and because this is the pivot this will go like that, yes. So I can now make some assumption about the direction. I can assume this end of the spring to move towards the left, ठीक है, and let's call that y, ठीक है, and let's call this point the displacement of this point towards the right as x, okay. So I can now say that y divided by L1 should give me x divided by L2, क्योंकि L1 and L2 both are distances from the pivot from the corresponding points, and they both should equal be relative to theta. कैसे? We assume theta to be small, so we assume the motion of the mass to be horizontal as well. तो ये जो mass का motion towards the right है, that because that will be L2 L2 theta, okay, L2 theta. So L2 theta is the displacement of the mass. Remember, this is the displacement of the spring. No, this is the displacement of the damping element. This is the displacement element of the spring. This L2 times theta is the displacement of the mass, and you can divide that by L3. Yeah, that's what I can do now. No, for the mass it will also be L3. Sorry, for the mass it will also be L3, क्योंकि ये pivot से जा रहा है ना, ठीक है. So this L3 will cancel out, which means that these two ratios are both equal to theta. And this is how I can connect x to theta by L2 theta and y by L1 theta. This will help us a lot. And now we can write down the equations. So यहाँ पे ये है कि we will, आपको याद है हमने दो तरीकों से इसको सॉल्व किया था. फ्री बॉडी डायग्राम, अब इसमें एक हम फोर्सेस के लिए करना पड़ेगा. So we have to take this rigid body and this rigid body और फिर इसकी forces और फिर हमें एक moments के लिए करना पड़ेगा. And you know that will get out of, I mean it is still manageable, but it is very easy to make mistakes. तो आसान तरीका मैंने कौन सा बताया था इस तरह की प्रॉब्लम को सॉल्व करने के लिए? The energy methods. And we can start with the Hamiltonian for simplicity. So write down the expression for kinetic energy, the expression for potential energy. Expression for kinetic energy is half m L3 theta dot squared. इसका ये है. And then we have to write down the expression for the rotational energy of inertia I, which is half I theta dot squared, which will be given है. और देखें ना यहाँ पे m जो कि पॉइंट मास है, तो और इसकी जो हमने ये ट्रांसलेशनल एनर्जी ली है, ये यही रोटेशन, यही इसके ऑर्बिटिंग मोशन है ना. इसका स्पिनिंग कोई नहीं है. अगर स्पिनिंग कर लेता तो हम इसके साथ वो स्पिनिंग का टर्म भी ऐड कर लेते. So it looks like translational kinetic energy, but because it's orbiting, something orbiting, उसका translational energy और उसका rotational कह दें, it's the same thing, ठीक है? Because there is no spin. For the potential energy, there are actually two possibilities. If you take the pivot as your reference, तो फिर इस जो है ना हमें ग्रेविटेशनल एनर्जी भी जो है ना हमें करनी पड़ेगी, but gravitational energy we can ignore by looking at this. When theta is small, all the motion is basically horizontal. When all the motion is horizontal, the gravitational potential energy is not going to change. So the change will be zero. और यहाँ पे जो कि हम सिर्फ changes की बात कर रहे हैं तो we simply go for k. जो gravitational impact है वो zero हो जाएगा. So we can simply write half k y squared, and that y we know is L1 theta. Okay, so that is L1 theta squared. And similarly, we will differentiate this, and we will differentiate this. We will find the expressions h equals k plus v. So we put a dot on both. So now we have these two expressions here, and this will be w dot non-conservative. W dot non-conservative will be the power associated with that element c. So c times square of the velocity, and square of the velocity we know is L2 times theta dot, and this will be your equation. इसको आप सिंप्लीफाई करेंगे तो आपके पास आपको इक्वेशन मिल जाएगा. ठीक है, the last one. Now this is simple, so you don't need energy methods for this. You simply need to write the free body diagram, and again you have to assume. अब यहाँ पे एक ट्रिक है. ट्रिक ये है कि this damper and this spring has a point in between, और उसका जो डिस्प्लेसमेंट है वो independent होगा. So let's call that z. ठीक है, उसको हम z कह देते हैं. So we will have two free body diagram, one free body diagram for m and one free body diagram for that point. Let's call that point A. Okay, so we will have that point A. So if this x is positive, so the reaction on the spring from the spring will be in this direction, which is k2 times x. That's easy. If we assume x to be greater than z, so this mass will try to pull the spring towards the right. The reaction on the mass will be opposite, which is c times, again this inequality means that we have to write x minus z, and dot because this is damping, yeah, and because this point A is on the other side, तो उस पे ये expression different होगा, same होगा और ये arrow different होगा. So c x dot minus z dot, and if we assume z to be greater than y, so this point A will try to pull the spring towards the right, and the opposing force will be, reaction force from the spring will be k1 times z minus y. And we can now write down the equations. Yeah, one for this one, because this is massless, so it is 0 times acceleration equals c times x dot minus z dot minus k1 times z minus y. Yeah, and the other equation will be for m. So m x double dot will be equal to k2x for the minus sign, and this is also minus. Yeah, don't worry about the minus, the too many minus signs. Okay, this is how you chose the assumption, the conventions, and these two equations. इनमें से सिर्फ ये करना है आपने कि because you introduce this as a dummy variable, so you have to eliminate this somehow. ठीक है, you have to combine these two equations in a way that z and z dot are eliminated, and that I think you should know. That was it for today.